In this video, we're going to go through some of the answers to the questions on the practice test and work through them so that you can check whether or not you've done them correctly. So for the first one, you have the hose, water hose scene. And you can say that the hose is pushing the water to the right. And at the same time, the water is pushing the hose to the left. And they are pushing at equal forces, even though the water and the hose might not have the same mass. And this clearly illustrates Newton's third law, because Newton's third law is every object, for every action, there is an opposite and equal reaction. Or for every force, there is an opposite and equal force. So for the next question, you have Santa on the sleigh, and you're asked to create force diagrams, force pairs for your situation. So we have the normal force of the sleigh and the ground. We have tension force between the reindeer and the sleigh. You can say we have frictional force between the reindeer and the hooves, the frictional force between the hooves and the ground. We have normal force between the hooves and the ground. We have gravitational force for all of these objects, and the list goes on. So what I asked you to do is to write these force pairs into a table. So the way that we can read this is that there is a normal force where the ground is pushing the sleigh up. So I usually like to skip the line. And as a force pair, that means that if the ground is pushing the sleigh up, then the sleigh is pushing the ground down. Okay, so those are those force pairs that we're talking about. I'm going to just verbally give you these here. So tension force you see because the sleigh is pulling on the reindeer to the right. The force pair would be then the sleigh or the reindeer pulling the sleigh to the left. Okay, and you can have gravitational force where you say that the earth is pulling the sleigh down, and then the other force pair for gravitational force is that you can say that the sleigh is pulling the earth up, and so forth. All right, so now let's go into ones that I know are a little bit more difficult for you. We're going to start by, first of all, drawing a picture. So here I have a boy, and he is pulling a wagon, and he's on the ground. So some of the givens we have, so that's the first part in using all my 5 things, especially for these force diagrams. I don't know what just happened here, but here's still my boy pulling the wagon. So for these force diagrams, you definitely want to have those pictures because then you can draw interactive diagrams. But I have the mass of the boy is 60 kilograms. The mass of the wagon is 15 kilograms. I also see that I have a value of 0.5 meters per second squared. I know that that's acceleration. And it tells me that the wagon has no friction. There's no air resistance. There's only friction between the boy and the sidewalk. So let's go ahead and I'm going to change colors and create some force pairs. I know there's normal force between the boy and the floor. I also know there's gravitational force between the boy and the center of the earth. Over here there's tension force, so between the boy and the wagon, and I was just told there was also frictional force. For the wagon, which is your second object of focus, I have from the wheels to the ground there's a normal force. There's also a gravitational force between the earth and the wagon, and there's the tension force. I was told there's no frictional force. So when you're drawing force diagrams, keep in mind that you are only going to draw vectors for forces that are touching that object. So if an object is touching another object, it is a force and gravitational force. So here I'm going to draw the boy. Here I'm going to draw the wagon. I like to start with the one that has the least number of force pairs. So if I look at the wagon and sort of circle it, I notice that I have a tension force on the wagon, normal, and gravity force. So let me start off with gravity force. Here's the force of gravity. And I know that the wagon is not moving up or down, so that's a normal force. And then the next thing I'm going to ask myself is, the wagon is being pulled. Which direction is it being pulled? The wagon is being pulled this direction through a force of tension. So now let's do the force pairs, and that's what we're going to add over here. Well, the force pair is that you have gravitational force from the earth onto the wagon. You have a normal force of the ground to the wagon, and you have tensional force from the boy to the wagon. All right, so there is my force pair. I know there's no frictional force, so I'm not going to draw anything here. So now let's work with the boy. Actually, let's work with the numbers over here. So a couple of things I know. Based on this, I know the mass of the wagon, which is 15 kilograms. So I know that I can find the force of gravity by doing mass times gravitational acceleration. And since the mass is 15 kilograms, gravitational acceleration, I'm going to use times 10 meters per second squared. That gives me my gravitational force, which is 150 newtons. So I know that this value is 150 newtons. Because these two opposing forces have to be balanced, I know that this normal force is going to be 150 newtons. Now the next challenge is trying to find out what this tension force is. And because I know that net force equals the absolute value of normal force minus frictional force, I also know that my frictional force, FF, equals 0 newtons. Okay, so I can use this F net, which is F net M times A, to find out what my what my actual tension force is. So I plug it into the equation. Again, 15 kilograms is my mass. The acceleration, it tells me, is 0.5 meters per second squared. And if I do this calculation, I should get a force of 7.5 newtons. Now I know this is the tension force because look up here. Remember, frictional force is 0. My net force is 7.5. What does in this case, tension force have to be? 7.5 minus 0 equals your net force. Now, knowing this here allows me to know instantly what my tension force is here because it is an opposite and equal force. So that means that the boy is feeling a tension force of also 7.5 newtons. So if the wagon is pulling the boy with 7.5 newtons, then the boy is pulling the wagon with 7.5 newtons. You notice they're both tension forces. They have to be the same type of force. You simply are just switching the force pairs. So we know this force right now. Having said that, I also know that we have the gravitational force. Now the boy is going to weigh more, so I need to make sure my vector looks longer. This is the gravitational force of the earth on the boy. And if I look at my data here, it looks like Fg is going to be 60 kilograms, that is his mass, times 10 meters per second squared. I again am using this formula. This gives me 600 newtons of force. That tells me that my normal force, and this should be going up perfectly vertically, but it is not. Normal force of the ground on the boy should also be 600 newtons. Now, we do know that there is a frictional force. So what is that frictional force? Well, I know my tension force is 7.5 newtons. all right? And I can calculate my net force being m times a. And I know that in this case, my mass is 60 kilograms, and 0.5 is what I have for meters per second squared. And if I do my calculation, that means I have a net force of 30 newtons. That means that the difference between these two has to be 30 newtons. In that case, this here has to have the value of 37.5, because if I subtract 37.5 by 7.5, I get 30 newtons of net force. And this here we can call frictional force between the ground and the buoy. And that solves that force diagram. So let's try one more. We're going to speed this along. In this case here, I'll just give you the answer. So I'm going to stop the video for it. So in this case, these are what your force pairs should be. A couple of things that are key in this here, you recognize they are at rest. And in this case, if I have a motorcycle, and I'll do my best to draw what looks like a motorcycle, not even close, but here I have a person sitting on that motorcycle, you notice that there are really only these two forces, nothing is being pushed horizontally, and so for that reason I'm only going to have two vectors, and those vectors, in fact, I apologize, in terms of the motorcycle, I still need to add the mass of the person, or the units over here. So this here should be this answer. There we go, 6,745 newtons, okay? And keep in mind it's at rest, that's why I know it's balanced. All right, we're gonna just do a couple of these here. I'll do the first one for you and then just give you the answers. You have a champion sumo wrestler. He has a mass of 200 kilograms. That is my M value. The figure skater has a mass of 40 kilograms. They collide, and we know that they have a force of 800 newtons net force. Okay? So in that case, what would the acceleration be for the sumo wrestler? So I know that F net equals m times a. In that case, we have 800 newtons. Then we have the mass of the sumo wrestler being 200 kilograms, and the acceleration is what we'd like to know. If you do your division, you'll see that it works out to be 4 meters per second squared. So what is the force of magnitude and the direction that Tara experiences? Well, if the sumo wrestler is exerting a force of 800 newtons to the right, then Tara is exerting 800 newtons of force to the left. Okay, what is Tara's acceleration? Well, we know that her force that she hits with is, again, F net equals m times a. She has a mass of 40 kilograms. If I do my calculations, 40, there we go. We should have an acceleration that's actually quite high of 20 meters per second squared. So I'll give you the answers for the rest of them that you can just check them and see whether or not you got them right.